All right. Let's get started here. So, morning stream, marking that as showed up, check. All right. So go down here. I can put a 1 here for now. Can I edit this? No. For some reason when it disconnects and reconnects, the Proton client is not as good as like Google's, which is fine. Just something to have to deal with. Okay, didn't spend any time in Brilliant today. I did my fitness check-in, I'm pretty sure. Let's double check that. Okay, let's go down here. Boom, 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 boom. Where's my fitness check-in? Home. Yep, I logged that this morning. HIIT I'm not doing today. 30 minutes of cardio. I haven't done any cardio today. And I haven't started on my dating apps. Okay. So let's do some Brilliant. Be a good warm-up. Just get some time in on Brilliant. And then let's look at what we have scheduled this week. So we have, I'm going to put here 3 so far. Can I do conditional coloring on this? Yellow to green. Let's do that. Format, conditional formatting, and add another rule. The range is going to go all the way to like what, O? But I can't type here, so I have to like drag it, unfortunately. And I'll leave off the last week of the quarter because why does that not work? Why can I not change that? Yeah, I mean Proton sometimes it sucks. Just be honest. Alright, so formatting rules. No, we want to do color scale from like red to green. And it's going to be min value that where it's red is like half the goal, which should be 9. So we'll say 9. Max point would be the full 18. And then we'll let them interpolate between the two. Actually, you know what? I'll do number 9 here, number 0 here. Make this one red as well. I think that color's a little bit better. Yeah. Okay. And then we will save that. Bam. Close that out. Okay, so we got 3 there. Making progress there. Making progress there. Yep. Okay, so these are all my recurring. And then I have spring cleaning stuff. That's not a super high priority. I might even delay that for next week. Yeah, let's schedule that to next week. I mean, ideally I would get it done this week, but I just don't want to do it, to be honest. I need to fix this thing now. Do the dotted right. There you go. Alright. So prepare for and plan travel, and then Linux binary analysis. So those are 2 things I got going on this week. My taxes are filed. I do have to do 1 thing on them. What's today? 14th, so it's tomorrow that they're like due. I have everything set up with direct withdrawal, but I have 2 states that I have to pay taxes on that I don't know if I have direct withdrawal set up. So I'm going to add that to my task list here. Just say read payment instructions for state taxes. And if we list out all our stuff, we'll say M plus advance on 9. Yeah. But, you know, I don't want to do that right now. I don't want to do any of this shit. The travel plans, the pavers from Home Depot, the spring cleaning, and the payment stuff for my taxes. I don't have to do any of it, and I don't want to do any of it. What I want to do is just study. Because it's been a couple of days since I got any solid studying time in. So I'm going to say let's add to the to-do list. Finish chapter 2 on the learning Linux binary analysis. Finish chapter 2 on learning Linux binary analysis. I don't think I have to quote that, but I'm going to do it and then say proj Linux binary analysis. And I can actually delete that if it's in that project. Okay. And then we say TLT start. I think just the TS 10. Ooh. Sorry, I had to sneeze there. All right, let's do that. So I think I have a PDF of this, right? Maybe not. Let's open up. Sorry, Finder. Oops. Go away, please. Go over here, Finder. Let's go to downloads. I don't think there is a PDF for this one. Yeah, I couldn't find one. Let me see if I can find one again. Learning Linux binary analysis PDF GitHub. GitHub is like the website for IT book piracy. Learning Linux binary analysis. What the fuck is this? All light books PDF. They didn't commit to the repo. They have links off to their shitty ass website. Okay. Learning. Maybe this is a PDF. .py? The fuck? Never heard of that. .py TLD. Is .py a TLD? A country code TLD? What is this? .py is Internet Country Code top level domain for Paraguay. I never knew this. It's great for Python projects. It is managed by NIC Paraguay and commonly used for websites that want to target or establish a presence within the country with subdomains like .com, .py for businesses and .edu.py for educational institutions. Registrations generally require a local presence or legal representative in Paraguay to boost local search rankings and improve trust among Paraguayan users. Yeah. It's being gatekept. I want it for my Python project. Is said to be publicly available domain name that anyone can register, but they only allow. Read more? No, I can't go on that website. It seems like they probably have it locked down, kind of like a co.uk type deal. Okay. Well, today I learned. I was not familiar with the .py TLD. Practical binary analysis? No. We're visualizing ELF binaries. That's interesting. So these are Windows binaries, but it says visualizing ELF binaries. These are portable executables. Why do people write shit in C# if it's for ELF binaries? Like, write it in like something that's not like corporately controlled piece of shit language that runs on a virtual machine. Like, there's so many great languages out there. Where's this thing? The project is an interactive binary visualization tool and a radical evolution of the traditional hex editor by translating binary information to a visual abstraction. Reverse engineers and forensic analysis can sift through mountains of arbitrary data in seconds. Even previously unseen instruction sets and data formats can be easily located and understood through their visual fingerprint. This is interesting. Cantor.dust. This is the one that I saw from XOR EAX Chris Domaz or whatever I think his name is. It looks something like that. A 3-dimensional visualization. Bin glide. What I really want is a tool that visualizes the address space. Like the entire virtual address space of a process. That would be fun to implement. It says entropy level. So it goes from ordered to random. BinViz, a Qt-based tool for visualizing arbitrary data. So I don't actually want to like visualize a binary per se. I want to visualize the virtual address space of a running process. But these tools look cool. What is this? That's trippy. That looks like some type of like astronomical photo or something. Anyways, none of this is actually finding what I was looking for, which is the actual binary or a PDF file for learning Linux binary analysis. Yeah, might be that I just can't find this book. Let's quote the book title. is this stuff? Workspace. Maybe here? Is this guy? This guy's probably not even at the. What is Stevens.edu? I never heard of that institution. Stevens.edu, Institute of Technology, 1870. Okay, where are they located? Why have I haven't heard of them? About. Oh, here it is. Hoboken, New Jersey. Okay. Never even heard of them. Oh, this is RE 101. Do you really need a syscall table reference? Ah, okay. It's kind of a nice table. It's only like 300. Yeah, 313 syscalls. I didn't realize break had such a low number. And mmap as well. And poll. Okay. Not familiar with lstat. I'm more familiar with fstat and stat. What is lstat? Let's bring up the man page. Lstat. Path is symbolic link, then it returns information with the link itself, not the file. Okay. Link stat. Select has a pretty low number. What about epoll? Is epoll low? Doesn't look like it. I guess because select and poll were like POSIX standards, they gave them lower numbers. Not implemented. Uselib. Okay. View text 202. Epoll. There we go. Old. Epoll weight, epoll create, epoll weight, and epoll CTL. They're in the 200s. K compare. What is kernel compare? Yeah, I want to go through. Is it Dupe 3? I didn't even know it was a Dupe 3. Everyone uses Dupe 2. Yeah, I want to go through at some point and categorize all of the syscalls for Linux AMD 64. It's only 313 here, so it's not like a huge project. But like categorize them, like, is this IO related? Is this like process control stuff? Is it, you know, IPC stuff? Is it like file system stuff? System stuff in general. Extended attributes have a shitload of syscalls. I didn't realize, because they have 3 variants here, and there's 3 different. There's set, get, and list with 3 variants. So there's 9 syscalls. That's pretty crazy. So that'd be like file system related extended attributes. And some of these, I mean, you could just kind of like group them all together. You don't need to have like separate entries for all these. Scheduling related, multiplexed IO. Is more IPC message queue stuff. File system iNotify related. This is IO. People I've never even heard of. pselect and people I haven't heard of. Splice, yeah, it's IO. Zero copy IO. T. Signal FD, that's one of my favorite syscalls. This gives you a file descriptor for the signals. Memory would be a big category. I consider pipes as a form of IPC. And then container stuff, set NS. Is C groups, if I search here, C group, C group. It's not even in the syscall interface. That's because C groups are managed as a virtual file system under, I think it's sys C groups. Sys C groups. Sysfs C groups. Yeah, there it is. Yeah, so these are different C groups here. Looks like these are created by systemd. .mount, .scope, .slice. Oh. Alright, clear. Close this out. Yeah, so lots of different syscalls. And be nice to get them all categorized. And then spend time kind of visiting each one, reading a little bit of the documentation. You don't have to read the whole man page, but like just reading a summary so you can properly categorize it. I think that would give me a really good understanding of the syscall interface. Like the dupe 3 I didn't even know about before I looked at this. I'm going to save this to my bookmarks. Or actually, you know what I'll do? I'll just jump over to learn log. Oops. And we'll vim up here. We'll jump over to projects. There's like a thing here. And I'll just link to add MD64. Okay. I just wanted to poke around some of these results. Wow, there's lots of lots of resources on this one. Linux ARIA 101. I'm curious, learn log. I put this under learning Linux binary analysis, but really it's like reverse engineering. Yeah, this is a man page that I want to read at some point. So there's man 2 syscall, which is this one. And then there's man 7 syscalls. I think it's man 7. Oh no, it's under 2 as well. There's syscall and syscalls. I guess that makes sense. It would be under 2 because 2 is all about syscalls. But yeah, man 7 is supposed to be like informational stuff. So if I go under here, there should be. So yeah, syscall and syscalls. Both of those I want to read at some point. Alright. I'm going to abandon the search for PDF here because I don't think it's going to happen. But yeah, I'm going to take a quick bio break and then I will start back where I left off in this chapter 2. Cool. Alright. Let's continue reading then, shall we? So, where do we leave off here? The last section, it's the section that we're on, is called elf relocations. Maybe I'll pick up reading on that. Turn the light on here. Yeah, let's start from this section just to get some more context here. So from the elf 5 man page, so if I do man 5 elf, okay, and this, if I just do man elf, does it give me the same thing? Yeah, okay. Man a elf, quits, yeah. So it's just the man page for elf, and it is 1,000 pages, 1,000 lines, I should say. These are all the types that are in it, the structs, different values. what different fields mean. Looks like it's pretty well documented, but there's a lot here. So alright, but yeah, this is from the ELF man pages. Relocation is the process of connecting symbolic references with symbolic definitions. Relocatable files must have information that describes how to modify their section contents, thus allowing executable and shared object files to hold the right information for a process program image. Relocation entries are these data. The process of relocation relies on symbols and sections, which is why we covered symbols and sections first. In relocations, there are relocation records, which essentially contain information about how to patch the code related to a given symbol. Relocations are literally a mechanism for binary patching, and even hot patching in memory when the dynamic linker is involved. The linker program, LD, that is used to create executable files and shared libraries must have some type of metadata that describes how to patch certain instructions. This metadata is stored as what we call relocation records. I will further explain relocations by using an example. Imagine having two object files linked together to create an executable. We have object 1.0 that contains the code to call a function named foo that is located in object 2.0. Both object 1 and object 2.0 are analyzed by the linker program and contain relocation records so that they may be linked to create a fully working executable program. Symbolic references will be resolved into symbolic definitions, but what does that even mean? Object files are relocatable code, which means that it is code that is meant to be relocated to a location at a given address within an executable segment. Before the relocation process happens, the code has symbols and code that will not properly function or cannot properly be referenced without first knowing their location in memory. These must be patched after the position of the instruction or symbol within the executable segment is known by the linker. Let's take a quick look at 64-bit relocation entry. So this is a typedef struct, ELF64 relocation. So it has an adder and an info, uint64t, called it rinfo, and then an adder, which is offset. In some relocation entries require an addendum or addend. So the addend, from reading this book before, can be either the memory value at the relocation site of the relocatable object, or it can be added as the relocation entry addend, which is just has a L64 relocation A, rel A. The R offset points to the location that requires the relocation action. A relocation action describes the details how to patch the code or data contained at R offset. The R info gives both a symbolic table index with respect to the relocation. The R info gives both the symbolic table index with respect to the location must be made and the type of relocation to apply. Okay, we'll take a look at that later, I guess. Because I'm wondering how they cram all that into a 64-bit integer. The R addend specifies a constant added to use to compute the value stored in the relocatable field. The relocation records for 32-bit ELF files are the same as for 64-bit, but use 32-bit integers. The following example are for object file code that will be compiled as 32-bit, so that we can demonstrate implicit addends, which are not as commonly used in 64-bit. An implicit addend occurs when the relocation entries are stored in ELF and rel type structures that don't contain an R addend field, and therefore the addend is stored in the relocation target itself. The 64-bit executables tend to use the ELF and rela structs that contain an explicit addend. I think it is worth understanding both scenarios, but implicit addends are a little more confusing. So it makes sense to bring light to this area. So let's look at source code function start underscore start just calls foo. Let's jump over to learning analytics binary analysis. What do we got going on here? Vim readme. So we're in relocations. CD into chapter 02. We'll just say cat test add-in. What did I do here? Okay. Make Vim makefile. Okay, so it's object code here, C23 static, no standard lib. Okay. And if I do file on build.o, 64-bit, obj dump disassemble build testaddon.o. Sorry. There we go. Now we see that calls the foo function. However, we see that it calls the foo function. However, the foo function is not located directly in the source code file. Upon compiling, there will be a relocation entry created that is necessary for later satisfying the symbolic reference. So if we do a disassembly on this, we can see, so they are doing a 32-bit compilation. So we should modify our makefile here to do 32-bit. How do I do that? I forget. 32 like that? Oops. GCC flag for 32-bit. Bit x86 binary on. Okay, M32, that's right. And then we do our obj dump on that. And let's compare this. So this is start. So we're pushing EBX, they push EBP. I wish they gave the compiler flags. Why does this have 2 calls? Huh? I don't get that. It just has a single call here to foo with the literal 3. So why is it doing 2 calls? Well, I guess these addresses are probably zeroed out, right? Okay, so we push EBX. Okay, here we go. So EBX, which is a callee saved register. So basically, we're saving it initially because we're going to use it later for some type of computation, and then we pop it at the end. So we subtract off 14, which is how many bytes? It's going to be 4 plus 16 would be 20 bytes total. And then we call 5 here, which is start plus 5, which is I don't understand this one. This call plus 5. 1, 2, 3, 1, 2, 3, 4, 5, which would be this memory address here. So it's doing some type of call here. Maybe this is for this thing. And then we add 2 to EBX, which is odd because EBX, like we don't know what EBX is. So adding 2 to it doesn't make sense. And then we push 3 onto the stack. That makes sense because you're doing stack-based arguments. This is not the same. I don't think you use these registers for arguments in x86 calling convention. Let's search for x86C calling convention. And then where's arguments? Cleans arguments from the stack. I guess there are different forms of this. Okay. But anyways, you push 3 and then we call here, which is start plus 12, which would be this address because this is 11. This would be 12. And then we add 18 onto the stack pointer again, which would not only remove the 14 we have here, but also the 4 that we popped or pushed onto the stack here. So we're resetting the stack back to where it was before here. And then we pop EBX, which was callee saved. And then we ret. So all of this makes sense here and here all makes sense. But I don't understand why we're calling into this thing and why we're adding 2 to EBX and then not using it. Yeah, I'll just give it the whole thing here. So I'm gonna ask AI, see if it can clarify that for me. Nice. Okay, so I get most of the lines from underscore start what they mean, but I have these questions about this ASM code. 1, what is EBX being used for? I guess I'll make it clear that it's a register. It appears that 2 is added to its value after it is pushed onto the stack is once, damn it, what the fuck? So stupid. It appears that 2 is being added to it after, what the fuck is this shit? Okay, I'm gonna copy this just to make sure. Okay. It appears that 2 is being added to it after it is pushed onto the stack. Once the push is complete, does that reset the value in the register to 0, or is it just adding 2 to an arbitrary to whatever value was previously in that register. I get that it is callee saved. Finally, what is it even being used for? Two. Why is there an additional call at byte 4? This call is not present in my code. Three. What the fuck, bro? I typed all that shit out and you're just gonna fucking... Okay. Jesus Christ. Almost lost my shit there. So the third thing is like, what is the stack space? What is the 0x14 bytes of stack space being used for? Because we subtract off here and then we add it back, and I get that we add it back because we push this onto the stack, which is needed for the call. But like, what is this stack space being used for? I don't think it was compiled with FPIC. Makefile. It wasn't compiled with FPIC. Okay, didn't copy. That's great. Love when shit just doesn't copy. There we go. So it uses EBX as a GOT base to call through. Emits this thing. Get PC thunk uses the call pop trick to get EIP. Okay. Let's go up here and start reading. Oh, it says or similar. What is EBX being used for? In 32-bit x86 PIC position independent code, EBX is commonly used as a base register for the global offset table. What is happening here? So we push EBX, we do a call to start plus 5, and then we add 2 to EBX. This sequence is a classic pick pattern. Call pushes the return address, EIP onto the stack. A helper XA6 get PC thunk loads the return address into RBX. What is that doing? So it's moving the value at ESP into EBX and returning. Okay. So that's what that call is. Why can't you just do that instruction end line though? Why do you need a function for that? Then add to adjust a point to the GOT base. Okay. Key clarifications. Okay. So it saves the call save register, restores it at the end, allocates the locals, which there are no locals, calls get PC thunk, which sets the instruction pointer. No, it just sets EBX to whatever is on the stack. You know what it is? It's no, can't be that. I don't get this because we're subtracting off, like 20 bytes. So we're allocating 20 bytes. So by the time we get to the call here, ESP is going to be set to something where it's pointing to a bunch of zeros. And if we dereference that, this is a move probably 4 bytes into EBX. It's going to be a bunch of zeros. So BX is probably EBX, the register. Oh, whoa, 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 whoa. It gets pushed on the stack and then we read it here. Oh. Wow, I didn't think about that. And it needs to be a function because the only way to read the instruction pointer is through the calling convention where the call puts it on the stack. That's like such a hack. Why not just allow people to read the instruction pointer?
it's 64-bit has instruction pointer relative addressing. Okay, so we're going to do this with no PIC then. Sub push call add ret. Sub push call add ret. This is a leave. EBP. So the base pointer. I think there's like a, in here we can say, hey, F frame pointer. Let's say GCC flag to use EBP as frame pointer. No omit frame pointer. Okay, push EBP, move ESP into EBP, sub, in my case 14, their case 8, ESP, push 3, oh, because I gave it an argument. Them test addend. I gave it an argument, but I don't need to do that. Oops, please stop. Push mov, ESP, EBP, sub, 8 ESP, call, then leave, then ret. Yep, so I got the same output as the book. Okay, so this information here is taken from the relocation entries and just put it in line there to kind of describe what's going on there. But it's doing a call to some address that will be patched as part of linking. Okay, so this value is little endian, -4, basically. So these are the relocation objects for that binary. Okay, so now we're back where we left off in the reading. Okay, relocation section, relocation.text at offset so and so contains 1 entries, which is a R386 PC32. Symbol name is foo. Offset 7. So I think as you see, a relocation field at offset 7 is specified by the relocation entry's offset field. R386 PC32 is a relocation type. To understand all these types, read the ELF specs. Each relocation type requires a different computation on the relocation target to be modified. So the R386 PC32 modifies the target with S plus A minus P, where it's S is the value of the symbol whose index resides at the relocation entry. A is the add-in found in the relocation entry. And P is the place, section, or offset of the address of storage unit being relocated. I don't even need these here. This is a void. I think it's a void. Oh, because I compiled it without standard lib? Hmm. So now these have addresses. So it's saying go ahead, go forward 2 bytes to here. So you can see that's foo. Computed address is here. It's not what is encoded, it's what's computed. And then here, just do a mov of this value into this location. Which takes out that many bytes to encode. It's pretty crazy. I guess you got 4 bytes for the immediate value. But it's C, which should just be as a numeric value, C is not require 4 bytes, it requires 1 nibble. So what are we using the rest of these? Here it is. That is our C there. So this must be memory address, yeah. 84, yeah, it's a little endian of the memory address. So this is our opcode for the mnemonic, move L. This is the address, and this is the immediate value. We get see the return. So we got push EBP mov ESP and EBP, sub 8 ESP, call E8 in the case of the book, that looks correct, leave ret. And there's 3 no-ops after this in the book, which aren't present in my disassembly. And then foo actually had a different implementation. So here they push EBP, they mov ESP into EBP. Okay. And they pop EBP. So literally they're doing nothing in foo. Okay. We can see that the call instruction, the relocation target at the memory address, has been modified with 32-bit offset value of of 5, which points to foo. Value 5 is the result of the 32-bit relocation action. To calculate an offset to a virtual address, use the following computation: address of call plus the offset plus 5, where 5 is the length of the call instruction. Which in this case, pay attention to this computation, as it is important to remember and can be used when calculating offsets to addresses frequently. An address may also be computed into an offset with the following computation: address minus address of call minus 4, where 4 is the length of the immediate operand to the call instruction, which is 32 bits. As mentioned previously, the ELF spec covers ELF relocations in depth, and we'll be visiting some of the types used in the dynamic linking in the next section, such as jump slot relocation entries. Okay. What do we got ahead of us? Got a lot of stuff. Chapter 2 lasts until 51, and we're on 35. And I'm not reading this very fast. So what do? I'm not really focused. I'm not really biased towards reading this right now. It's a bunch of memory address math that's like super not interesting to me. Let's go back over here. Okay, I'm gonna take a break here because I'm just not able to focus. And I'd rather just take a break. So let's say 11:30. Got an hour and a half in, maybe an hour of reading. Not really a lot, but it is what it is. And then I'll do my lunch back when I originally intended. Okay. I'll be back on at 1 p.m. after I do my lunch and cardio, but I just need to take an early break here because I can't focus on this stuff.